is integrate both geographic data so that you can see where the most prevalent cases of flu are happening within this particular region, as well as additional data sets from outside of this health system. These are public weather data sets that are available on top of Google Cloud Platform for anybody to integrate into their clinical or operational types of analysis. And so here we're integrating NOAA weather data to look at snowfall and precipitation and understand how those track to the different case rates that we see of flu. Underneath our cloud CDW is Google BigQuery. And Google BigQuery is an incredibly powerful managed database for analytics. It's a columnar database, so it works very, very fast, very, very efficiently at analyzing great big chunks of data and analyzing time series types of data that we often see within the healthcare space. It's fully managed, which means that you don't need to worry about the infrastructure for it. You just go straight to cloud.google.com/BigQuery, and it's there ready for you to use. And it's safer because we automatically encrypt all of the data that's in BigQuery, and the way that we set up projects on BigQuery as part of Cloud CDW enables you to meet your HIPAA compliance needs as well. So we have deployment manager templates that are set up BigQuery projects and Google Cloud projects in a way that helps you to satisfy your HIPAA requirements. In addition, because we have these public and commercial data sets available, you can integrate these into the analysis you're doing, and I'll show you some examples of those different data sets as well. But most powerfully, it's scalable. So you can throw petabytes of data at this and it doesn't blink. Behind the scenes, it scales up horizontally, so it's looking ahead at the analysis you're trying to do and just brings additional machines, additional compute power to bear as it sees that you need it. And interestingly, for a columnar database, everything is queryable through SQL, which means that we have a host of different tools that you can use on top of BigQuery directly for doing your business intelligence and your visualization. Google has its own Google Data Studio, but in addition, all of these different ones up here are shown as well, and these all have direct integrations into BigQuery. The dashboard. Ooh. We're in the horror movie today, can you tell? I shall just, thank you.
Hang out here.
Yeah, the dashboard that you, oh, we're not up there though. Well, the dashboard that you saw before was created with Looker, but we've also created dashboards using Tableau and using MicroStrategy and others as well.
All right, you're back up.
Thank you. If you don't mind staying here and just wobbling it occasionally. Yep. Thank you. Chief Wobbler. So, as you've probably heard this week, we've been delighted to announce that our healthcare API has moved to beta. And what that means is now you can ingest healthcare data into Google Cloud Platform in its native formats. In Fire, not too many people yet are using Fire, ingesting it directly in Fire form into Google Cloud Platform, but we're starting to see that as customers are upgrading their EMR versions to the latest versions that support Fire interfaces. Most of the data that we see coming from EHRs today comes to us in HL7 version 2 format, and that's part of the Cloud Healthcare API as well. And in addition, we also support DICOM images, so any medical radiology types of image that you have can also be ingested natively in this format directly onto Google Cloud Platform. And then what I'm showing on the right-hand side is just a simple SQL statement that's joining EHR and imaging data together. And this is the type of cross-modality data analysis you can do once you've got all your data together in BigQuery. So that sounds lovely and easy. We all know in practice that every single data source is different from the next. And I always like to say imaging data is nice and large. It's relatively simple. EHR data, small and messy. And so when we think about harmonizing data, we think about the bulk historical data that you want to bring into a cloud CDW, as well as the incremental or streaming sources that you're bringing in. And typically for your bulk data, those are in CSV formats, or it's some kind of direct connection through to an external database. But for incremental data, as well as those types of source, it might also be an HL7 version 2 messages, or FHIR messages, or other types of streaming data like that. And what we need to do in order to harmonize this data is think about 4 key aspects. Harmonizing the field mappings, so understanding the source schemas that you're coming from, multiple schemas, what your target schema is within your cloud CDW, and I'll talk a little bit about that in a minute. And then thinking about how you map those schemas, the fields between them, in order that when you say patient over here and PAT ID over there and PT ID over there, they all go to the right patient ID that you've defined within BigQuery. The next area is terminology mappings, because we all know that particularly when you acquire a new hospital into your health system or a new clinic into your health system, or maybe because you're trying to integrate data from lots of different sources that are messier, then different sources use different terminologies. Let me give you an example. I've worked with health systems where some of the medication data has been in RX norm, but other medication data has been in FDB because one particular hospital relies on FDB as its medication vocabulary. And so understanding how you convert between these different terminologies is also something that you need to do as you harmonize this data. The next area is around units alignments. If any of you have ever visited a NICU, you'll know that the weight of babies, of neonate babies, is often weighed in grams, whereas the weight of the adult patients in other ICUs within that same health system is typically measured in kilos, if we're lucky, or pounds, more commonly. And so aligning the units as well becomes really important, not just for things like maths, but also for things like labs as well. And then clinical entity extraction. I think we've all become very familiar with physician burnout and understanding how how physicians like to either dictate or type up their note. And so extracting out the richness of that data into the structured data, augmenting the structured data with the wealth of information that's often buried within the clinical notes from the providers, becomes really important. Now today, you can do all of this in Cloud CDW, but you have to do it manually. And so the tools that we're working on will help to automate a lot of this, and over time, add machine learning to it so that it can start to suggest the mappings to you. Over on the right-hand side here are the target schemas. So just as we recognize healthcare data in its native formats as first-class citizens, we also recognize certain schemas that are typically used for healthcare analysis as first-class citizens as well. And starting at the top there is FHIR. So if you're looking for a way to start converting to FHIR, converting your data to FHIR, this gives you a path to that. The second one listed here is OMOP, the OMOP Common Data Model, which Greg Klebanov is going to talk a bit more about in a moment. And then underneath I2B2 and CDISC, and frankly, any other schema, because we all know that many health systems, or for certain analyses, there are always schemas that already exist that people need to continue using, at least for a while. So you don't need to change the approach you're taking in order to leverage Cloud CDW. So right now, FHIR and OMOP exist as target schemas within Cloud CDW, as well as the custom schemas. They exist as well, and then we'll be adding CDISC and I2B2 over time. Of course, you set up your data harmonization rules, and then everything changes. Your source changes, maybe your source schema changes, Epic releases a new version, Cerner releases a new version, your vocabularies change because they're always being updated, or your target schema changes. Everything changes along the way. And so you need to be watching for those changes. And so around this data harmonization and all these transformations is the framework to enable you to monitor and to manage lifecycle changes within this. And included within that, something that we're starting to work on now, is understanding when data is exceptioned, but also what limits of exception you will allow through with warnings versus what things will really alert you because you need to do something about that. And we're leveraging the concepts of statistical process control, which is very common within manufacturing industry, in order to help drive that decision making around when to alert, when to warn, when to let pass through. And the lifecycle management becomes critical because from a data provenance perspective, when you're looking to try and track back the data, then you also need to understand where that data came from. And so understanding which version of the data harmonization was in place at that time and exactly what that transformation was, where the sources of data were that came, that becomes really important. I mentioned the public data sets before. We now have over 100 public data sets available on BigQuery that you can just integrate into any analysis, join as tables into any analysis that you're doing on BigQuery. These are some of the healthcare and life science ones available. There's a bunch of biomedical data sets that we're bringing on as part of the NIH STRIDES initiative. And then there's a fair bit of Medicare and Medicaid data from CMS. But we're also always in the process of adding more data sets. And right now, my focus is trying to ensure that we add more social determinants of health data sets that will help with the analysis that you're trying to do within your populations. Once you've harmonized all that data, what do you want to do with it? Maybe you just want to create some kind of dashboard, some kinds of analytics that will help you understand things like the longitudinal patient record. Or maybe you need to create analytics that are portable. So I think about defining cohorts of patients in the same way that I think about needing to enable clinicians to do those definitions in terms that they understand. So not looking at the detailed fields and saying, I want to select on this field and I need to join it with that thing over there, but rather enabling a user interface that clinicians can say, look, these are my inclusion criteria and these are my exclusion criteria, and be able to leverage common definitions for things like certain conditions, leveraging clinical quality metric definitions, leveraging other common definitions that are out there in our industry. And so you'll be able to create your cohort definitions, and underneath these will be made portable so that you can then apply those cohort definitions to any data set that could be enabled within FHIR. So this becomes really powerful for you because it helps to protect your investment. As well as cohort definitions, you can think of query definitions and metric definitions in the same way. So we'll be couching behind the scenes these definitions within FHIR, and of course will help you get to FHIR, so that way, if you bring on another data set, all you need to do is realign it to FHIR and then apply that definition on top of it. And that could be a query, that could be a metric, that could be a cohort. And over time, we'll also enable you to share these definitions with others as well. And so that too helps, particularly in the research world, particularly as you're looking at doing more collaboration with others in your field. Another reason why people want to bring all of this data together, and I've spent quite a bit of time this week talking to several people about this, is in order to use it for machine learning, in order to use it either to train a model or, more often right now, to be able to infer data, to be able to predict data using somebody else's model. Well, we'll meet you where you are. We have a range of different machine learning tools, APIs, and techniques that can help you. And all of these work directly on top of BigQuery and on top of our cloud CDW. Over on your left are the ones that require more engineering, so things like TensorFlow or being able to leverage Spark ML, Cloud CMLE. In the middle are some of the predefined models that we have available. So for example, our natural language API, our video intelligence API, and also our translation API. And then over on the right, BigQuery ML, which so far is primarily for classification and regressions, but over time may expand as well in its capabilities. So if you want to train machine learning models, bring it on. Bring it into Cloud CDW and then have all of these different tools available for you to do that. Now, if you're trying to apply somebody else's models on top of the data in Cloud CDW, we'll help you do that too. So our framework will let you invoke other machine learning APIs as well to make those predictions. Finally, you've done that, and in some cases, that's it, right? You're using that data internally. In other cases, particularly in some research cases, you want to de-identify that data in order to make it available to researchers. And so the de-identification API is the first step on the way to being able to share those data sets more broadly with other researchers. We have other things in the works there as well, but this is what's available right now. And this de-identification works not just on structured data, that's relatively easy, but also on imaging data. So if there is PHI burned into the medical image pixels, which there often is, and it also works on unstructured clinical notes as well. And in addition, on the structured data, if you already have some de-identified data, we can now present back to you the risk of re-identification of that data as well, so that you can understand where the risk lies on a spectrum. I talked a little bit about this actually last year when I said I think we'd run 3 datathons at that point on GCP and had I think another 6 coming up in the next year. Well, that proliferated. They bred like bunnies, and we've actually supported now 11 over the last year. These are a great way to get your team's direct experience of using GCP with healthcare data. They're held around the world. If anybody would like more information, come up and see us at the end. But this is essentially a little package that allows organizers to host healthcare datathons in an appropriate environment for that. And so if you want to host a datathon, come up and see us. Just bring your data set to us and we're happy to help get that set up with you. Or if you are interested in attending them or having one of your team attend one, let us know as well. Typically what happens is over the course of a weekend, everybody gets together and really blats out clinical data science on top of BigQuery and on top using data science tools. So with that, I'd like to hand over to Josh, who's going to talk about, on the data ingestion process, how you take that data, X12 data in this case, and convert it into FHIR. And with Josh is Alan as well. Thank you.
Thank you, Marianne. Is everybody excited to take a look at a deep dive at the clinical data hiding in X12 ANSI format? Woohoo! Yes. All right. So as some of you may know, CareCloud is a electronic practice management and electronic medical record system platform entirely hosted in the cloud. And one of the reasons why we're here with you guys today is we've been a technology partner working with the GCP team, particularly on the healthcare API for the better part of the last year. So going through the various alpha phases. And one of the things that we've been able to do that we want to demonstrate for you today, as Marianne mentioned, all of the great power and insight that you can gain from your data, having it formatted in Fire and having it prepared for prediction. This is an example of how that can be done, and frankly, how easy it looks once you've taken the time to build that out in your own systems. So, how many people in here are familiar with X12 and have dealt with that as a data format? Show of hands. Okay, not that many people. We'll dive into what it's used for, but primarily this is the way that electronic practice management systems, medical record systems, big pharmacy, benefit management companies transact between each other, right? This is a 40-year-old interoperability format. We were both born in 1979. That's why I like X12. But it's in use quite prevalently across all of the big payers, right? And what that means is a lot of the data that we want to analyze longitudinally, especially when you think about the clinical perspective, is locked up in these really old archival data formats. So Fire coming around, and now with Fire v4, we're standardizing on a normative model that is going to allow us to essentially continue with backward compatibility, have this normative format that we can do analysis on. So CareCloud, because of the way that we service our existing provider customers, already has invested a lot of technology and know-how into translating very specific detailed data, in this case bidirectionally, right? So we're talking about fully interoperable, bidirectional, semantic translation of data from the various components of X12 messages into the equivalent Fire resource. That's a mouthful, so we're going to actually pop into a demonstration to kind of show how easy it is once it's been put into practice. Alan Polito here is our technical lead, whose team did all the development, so he's up here making it happen. So this is our console. We're announcing here at the conference the beta of this as part of the beta for the healthcare API. So this is going to be available through the marketplace, or working with us, we can offer this as a managed service or a SaaS offering. But we're going to go through how simple the configuration is to go from an X12 archive into Fire resources in the Google Healthcare API, right? So we're going to start off. We're going to go through and configure a tenant, right? And if you think about the various different ways that X12 can be managed inside an organization, you might have dozens or hundreds of different X12 definitions for a single message type in a large payer organization. So in this case, we're going to say we have options for the sources during the beta. GCS is obviously our favorite, but if you're looking to move into the Google Healthcare API from somebody else, those are available as well. If we pop over, it's as simple as basically configuring the bucket that you want to pull the data out of, and targeting your Fire server. In this case, it's the Google Healthcare API, right? I'll do another quick survey before we kick this next part off. How many of you have your own Fire servers, or have a team of engineers back home that are trying to build your own Fire solution? Okay. Even if you're not, go back home and tell everybody to stop doing that, right? We've been, I'll testify for a second from just personal experience. We went through a lot of the open source projects, evaluated nearly all of them, went so far as to even look at developing our own cloud-hosted Fire server in-house. Really, when you look at the amount of raw engineering that it takes to get that all the way through, take advantage of the work that Kurt is doing. That team is really strong. They're really committed to maintaining the standard. And frankly, the service is really performant as we've gotten through the various phases of the alpha. It's really at a place where it's enterprise grade production strength. You can really pump a lot of data through it. So we're going to go ahead and trigger a sweep of all of the, in this case, 837 claims. So this is, well, we talked about how many people had ever seen an 837, so we're going to give you a sneak peek at what that actually looks like. So if you're a COBOL programmer, if you like mainframes, this is what we love. But locked in here is all of the valuable procedures that were performed on the patient, the related diagnoses that were used as the supporting clinical rationale for why that procedure was performed, all of the patient detailed demographics, right? It's a very good, dense data format, 40 years ago when you really needed to transact between mainframes. And frankly, there's billions of dollars of existing investment in keeping this format operational. And this is frankly the backbone of the way that we process medical claims in the US. So if we go back, again, thinking about the power of the way GCP allows us to build data pipelines and do these types of transformations. We can do this at batch or in a streaming fashion, right? So as these X12 messages are being generated, we can translate them on the fly. Now, if you roll this forward, now as more and more of our industry is standardizing on FHIR as the primary data format, this type of semantic translation allows us to take the FHIR resource and translate it now back into X12, which is the format that your mainframes are typically going to be processing. So we can pop in and we call it a human readable X12 message. And that means that, really you're an analyst that specializes in looking at these types of data. But breaking it out by the various loops and segments, you can see kind of the nested hierarchy, the way this data gets generated, right? And again, we're talking about that full fidelity capability of translating it on the wire. We have another legacy format, if you guys are familiar with this. This is a CMS 1500. But, again, you think about the power of being able to have this type of semantic mapping. You can just, talk about processing images. We can generate the CMS 1500 claim form directly from what would have been an electronic claim submission. Now, the real power and where this flows into the clinical data analysis is being able to get into the FHIR resource itself. So if you're thinking about modern development languages, modern programming techniques, most folks are not going to be building those applications and those capabilities against that native X12 format. But there is a semantic mapping and there is a way of representing it as a FHIR resource. In this case, we can go down and take a look at we'll take a look at the diagnosis, or do you want to look at the claim ID, right? So again, we're talking about bringing this from a legacy or an archival claim storage, right? FHIR is really good at being able to identify resources across systems, right? And if you're bringing something out of a legacy system, maintaining the identity integrity from the system that generated it, and as you move it out to the FHIR server, being able to reference it without having to copy it, right? And for all of us here, as true believers in clinical data analysis and healthcare IT in general, right? This allows us, as Marianne mentioned, as we're publishing data sets, as we're evolving our ability to make this data useful and available, we can leave that data in the resident FHIR server, right, where the entity that's responsible for managing it is, and we can reference it through FHIR, right? And so that's really our goal here, is to maintain that identity integrity. So the other great part is now, if you think about the way EMRs and everybody are building the supporting information clinically, that all gets represented in FHIR as a procedure code and a diagnosis code, right? And they're mapped here so that you have the linked diagnosis with all of the procedures that were performed on the patient. And now, in our case, I know we mentioned a few other EMRs, but some EMRs out there are generating their clinical data in a FHIR compatible format. So, as these things evolve, now this is really where we can start to find out things totally new, right? maybe there's a propensity to not go to your follow-up appointment after your last claim was denied, right? Now, if you're putting these data together, you can start to map out how patients were treated against how the financial information was actually transacted between the patient and their insurance company. We'll give you a little, okay, good there. We'll pop back to the slides. Yep. The joys of AV. Okay. So, the last bit, you know, we have to have a ubiquitous architecture slide, or it doesn't seem like anybody's doing anything. So the idea is that all of these pipelines are built in GCP, right? We're talking about using the same you know, powerful tools that Marianne mentioned. That's everything that transacted there, right? Going from GCP as or GCS as the source data format, moving through data flow. You can take the picture, but you need the Edison engine in the middle there to actually do the semantic translation. But you know, this really does work at scale, right? We've tested this into the millions of messages generating. We did an interesting conversion with a data set that we might potentially open source, where we created 4.3 million FHIR resource bundles out of the NPPES data set that's publicly available in BigQuery. It ran in about 15 minutes. So it's, you know, and that's in a single data flow pipeline. These are really powerful tools that are really ready to handle our scale of data. You know, in this case now, all of the data that we've ingested is prepared and ready in the FHIR API to be leveraged by all of the other capabilities that folks have been talking about. So, you know, all of this is key, right? So, what we're asking here, coming out of this, if you have any questions or you'd like to participate in the beta, if you can follow up with any of us after the program, we're looking for folks that are potentially looking to leverage GKE on-prem, right? Because all of this is being deployed in Kubernetes. So you can either host it in your GCP project in your own Kubernetes container. We can host it in Kubernetes for you also. But you know, we think that a lot of big healthcare institutions are going to be keen on trying out GKE on-prem in their own VMware infrastructure. We think that's going to have some pretty significant mechanical advantages too, to have the data translation process as close to the archival data as possible. And then, you know, as you think about moving out to the cloud and moving from those on-prem or co-locations out to GCP, you know, that data is already in GCP prep for you in the healthcare API. So with that, I'll hand it back to Marianne.
Thank you very much. So that's showing a real example of how you can use GCP to convert that claims data to FHIR. Kate, can you, I don't know how I'm doing this. Great. And so, actually, I think we want to go back to the slides first. Sorry. And so, next up is Greg Klebanov, CTO of Odysseus Data Services. We talked about OMOP as being one of those standard schemas. Greg's going to talk more about that. Thank you, Greg.
Hello, everybody. I'm Greg Klebanov. I'm the CTO at Odysseus Data Services. I can't really see you, but I know you're there and you can see me. So today I will demo a tool that was developed and been maintained by the open science, open source community called Odyssey. And before I even dive into this demo, I'd like to put this tool in what we do in the context of Odyssey as an open science community. So Odyssey, it's pronounced as Odyssey, it's spelled OHDSI, stands for Observational Health Data Sciences and Informatics, is again, an international open science, open source community that is focused on enabling standardized, reproducible, scalable, observational data analytics across the world. And would like to stress that Odyssey is an open source, open science community, meaning it's public, it's open, it's international, and anybody can join, anybody can contribute, and anybody can use any of the tools and standards and methods that are developed by this community. It's worth mentioning that Columbia University is is a coordinating center across the world. So as you can see, Odyssey is a global community. It spawns multiple countries, multiple continents, and today you can see the statistics. It's grown quite nicely, and we work very closely with our partners and collaborators in US, in Europe, and in Asia, including South Korea and China. So the mission of Odyssey is really improve public health by enabling better healthcare decisions based on evidence produced from real-world data sets. And so one of the, apologies for that. So Odyssey, again, is an open science, open source community that enabled key open standards, including a standard it's called OMAP CDM, Common Data Model. That's what CDM stands for. And the latest version, version 6, you can see it on the screen, is quite mature, quite nicely developed. So in addition to a common data model, Odyssey also enabled a set of standardized medical vocabularies and a set of standardized tools. And one of those tools is Atlas, and I'll show it to you today. But before I dive into Atlas, I just like to maybe talk a little bit about the data journey of how this data gets into data analytics platforms like Atlas. So data sets, what kind of data sets are we working with? We're working with clinical data sets, or we call it real-world data, that comes from different types of organizations that come from, they could be medical insurance claims or electronic medical records. They could be lab results, survey data, clinical trial data, chart reviews, and so on. So any types of data that is coming from a clinical utilization of drugs and treatments, we essentially need to process and convert it into a standardized format called OMAP CDM. So what's nice about OMAP CDM, it creates a single standardized way of saving data so that data scientists or researchers only have to design their query once, and then it can guarantee that this query is going to run on any OMAP CDM database across the world. And I'm really excited to say that we added, so Atlas and any other tools in Odyssey, they supported, I believe, close to 9 different data sets, databases. And I'm really excited to say that we also now provide support for GCP platform, including big data, BigQuery database. So what you see on the screen is essentially is a simplified architecture of how we process data to convert it into OMAP CDM, and we've successfully converted data sets, actually pretty large data sets, utilizing Dataproc and Apache Spark. So it's also worth mentioning that the data sets that we're working with are very, very large in size. So they can be very, very large. They, again, medical claims data tend to grow on data aggregators such as IBM True and MarketScan databases can tend to be over 200 million patients in size for a single database. So it would typically mean tens of billions of records that need to be processed and converted into OMAP CDM. I'm also very excited to say that Odyssey Atlas, which is, oops, I don't know what happened here. Odyssey Atlas, that is probably one of the most common and popular tools in the Odyssey community, also now supports BigQuery database underneath, and I'll give you a little demo of that tool in a second. So Atlas is a tool that was produced and is produced and developed by Odyssey community. So my company, Odysseus Data Services, we're one of the most active contributors in developing this tool. And Atlas is a tool that was designed to enable researchers, data science, with an ability to design complex analysis studies and then execute those studies on the top of OMAP CDM database. Okay. I need some magic here. Great. So got 2 hands, so bear with me 1 second. So what you see right now on the screen is the latest release of Odyssey Atlas tool. And the tool is actually quite mature at this point and quite sophisticated. It offers multiple quite nice features, including full database level characteristics, which you will find, like, for some reason, don't see the mouse. Oh, here we go. It's called Achilles. So Achilles is a full level, database level characterization of your data set. So you can imagine that before a scientist even begins to design their study and research, they would like to know what's available in a database, and this information should be coming from Achilles. So Achilles allows you, as a researcher, to see data stratified into different types of dimensions that are available in OMAP CDM, including it will give you dashboard information, demographics information, visit information, conditions information, procedures, drug exposures, measurements, and so on. So it's for any researcher, it's very, very easy to come to Achilles and just look up if this specific database contains information about a condition / disease or a drug of their interest before they even run a complex analytics inquiry. So another secret sauce in OMAP CDM is a set of standardized medical vocabularies. As Marianne previously said, drugs can be coded in many different ways, and the different RX norm exist, and CD vocabularies exist. So one of the most fundamental standards and decisions that Odyssey made is that they decided to standardize. So what our team is actually doing, they bring together multiple medical vocabularies, and they standardize on a single representation of a drug, on a single representation of a condition, so that when data is being converted from raw data into OMAP CDM, data is being converted into standardized representation of that condition or a drug. So here, in Atlas, you'll be able, as a researcher, to search and browse medical vocabularies. So cohort, any mature analytical tool offers today a cohort builder, cohort designer of some sort. And so Atlas is probably one of the most sophisticated tools that been developed in the industry. So it allows you as a researcher to design a very sophisticated cohort information. Not only you can design a cohort, and I got some examples that I'm going to show you in a second, but you can also, as you design your cohort, you obviously take advantage of standardized medical vocabularies, and then you can execute some basic statistics immediately by utilizing this cohort. So for example, I've generated some counts. I designed a cohort that is meaningful to me. So it's ibuprofen being taken by a male over 40 years old. And I ran it against the CMS data set. So SynPath is a synthetic data set representation of CMS data, claims data. And I can immediately see that my cohort resulted in 77,000 patients that would fit the cohort. And I immediately see how my filters, my criteria, limited cohort selection at the end. So cohort are the building blocks in any data analytics tool. And again, as you can see, this is running against the BigQuery database. So, and then it gets more complicated. Of course, as scientists, they continue their research, they would like to know not only how many patients do exist in a specific data sets, but they would like to get a full characterization of that cohort. Characterization meaning take this cohort and stratify it by different dimensions, by different that exist in OMAP CDM data set. So for example, in this case, specific case, I actually took two cohorts, one aspirin users and one ibuprofen users, and I put them against one another. For some reason, I can't scroll again. Here we go. Right, so as you can see, I can now characterize my cohort by different criteria that I'm able as a researcher to select. Then, as one of the latest features that was added in Atlas is a treatment pathway. So especially treatment pathways are very important when, for example, oncology patients going through a treatment, and it's very often when oncology patients going through a treatment, they go through a multiple specific predefined treatment pathway. So in this specific case, actually, it's not talking about oncology, it's talking about diabetes too. But you can see a pathway of treatment of different patients, of how they go from drug 1 into drug 2 into drug 3 throughout their journey. Incident rates, basically incident rates provide exactly what it means, is the incident of certain outcomes in the set of cohort patients. So in this specific case, it's an incident of Not even sure what that means. But I'm sorry, can't see it here. Right. So you can also see a more complicated analysis, estimation and prediction analysis. So estimation is again is a relative risk of something happening based on your data set. In a more complicated case, just recently added is a patient-level prediction analysis. So patient-level prediction basically is a probability of something happening for a very specific type of a patient, probability of developing certain condition in the future. So patient-level prediction is just an example of, again, a personalized treatment that is possible today to develop for different patients. So I know I have a very limited time, and Atlas, as you can see, is a pretty extensive tool. Again, I'm really excited to say that now Atlas supports BigQuery as a database. And the last words I would like to say that, again, whatever you saw today, Atlas is an open source tool, so anybody can come, anybody can join the community, contribute, reuse it. And thank you for your attention.
Great, thank you very much, Greg. So to wrap up, maybe, there we go. Sort of my closing message for you really is start bringing your healthcare and life science data onto Google Cloud. Start thinking about the analytics that you want to do. Start thinking about the harmonizations that you need to do and where you want that data. Do you want it in Fire, persisted on GCP, as Care Cloud has talked about? Do you want to bring it into a specific target schema to enable collaboration with others, as Greg has talked about? Most importantly, you can get started now, but plan ahead for scale and think about how some of the tools that we're building might help you do that kind of data alignment.